Hey, Kaylin, how are we doing? We've got the first question of the day. It is sorry, I'm a little congested. The histogram shows the distribution of the mean ACT scores. Let's go check that out here. I did it a little bit quietly. Seem to be doing better. Less congestion. That's what we like. Okay. The accompanying histogram. Go. Stat 201, Chapter 5, Homework, Part 2, the accompanying histogram. Let's go take a look at that. I think this one has like percentiles on it, doesn't it? Okay. Pearson. Didn't it autocomplete? There it is. How's everyone doing today? No, don't want to be congested. See, good, awesome. Yubatswake Shinna, good to see you here. Assignment manager. Let's go check this out. Chapter 5, Part 2, Homework. Oh, I see it right there. Okay. Let's go check it out. So how are we going to solve these problems right here? Well, these types of problems on the test, a lot of people wonder how would this look on the test. To see what these would look like on the test, go to Review 1 or look at Canvas content. So Review 1 has what the question 4? What's question 4? Boop. Oh, there we go. Ah, thank you so much, Kaylin, right here. Yeah, I saw ACT. I saw ACT in this one. And I was like, oh, that's the ACT problem. Nope. This one. Here, let's check it out. Okay. For this one right here, we've got different scores from different groups. Now, take a look. Does this look normal? Does this look normal? Yes or no? And why? So does this look normal? What do you think? What do you think on does this look normal? If it looks normal, it should look unimodal symmetric. It should look unimodal symmetric. Where's my copy paste? There it is. Should look unimodal symmetric. So let's check this out. There's two problems with this. There's two problems. So if it looks normal, it should look unimodal symmetric. So what are the two problems with this? It's bimodal, exactly. It's got a second mode down there, and that is also leading to a lack of symmetry. So I've drawn the normal with the yellow highlighter, and I've drawn over it, so that's the normal right there. And then I've drawn the other one in black right there with what it actually kind of looks like. So when we take a look at this data right here, it wants us to give, I think, two reasons it's not normal. So it's not really just fully skewed to the right. If you look at these answers right here, you see 68. This is going to the empirical rule. 68 is how many standard deviations? When we talk about the central 68% of data, that's within how many standard deviations? The central 68% of data. Here we go. The middle 68 is within how many standard deviations? We've got a lot of drawings. Ooh, there we go. That's a good one. The middle 68% should be within how many standard deviations? So this one basically gives away part of the other questions right here, because when we're talking about within so many standard deviations, we can talk about these z-scores, which are the standard deviations 1, 2, 3. Great job, Kaylin, right there. We got 3 more points. And then we can do the context of the curve also with the numbers. You always want to draw out the context and the z-scores. That's a big thing I think people don't do, is they don't draw out the curve. So right here on the bottom, we should see something like 0, 1, 2, 3, 1, 2, 3. And this is just an estimate right here. But the problem is down there on the bottom, we're going to see issues. And 68% would be contained within plus or minus 1, 95% within plus or minus 2. So this one's wrong right here because it should say 2 standard deviations. So that's a wrong answer. We basically did process of elimination. We'll look at that second answer right there. But it's not right skew. It has a second lower mode. Maybe it's not really skew. It's just a second lower mode, I would say. If the data, and there we go, if the data are bimodal, which we noticed right there, a lower and higher mode. So this now gets into the normal probability plots. For normal probability plots, how do they look? This is a very important thing to know what a normal probability plot is. Why do we have a normal probability plot? Why do we use normal probability plots? What is the point of a normal probability plot? Well, the name of a normal probability plot tells you what it is. It's a plot to check the probability that something is normal. Let's write it down here again. A normal probability plot. So it's a plot that is used to tell the probability something is normal. So if we have data, and I am creating random normal data right here. So this is random normal data, 1,000 observations. You don't have to know how to code, but we can make a histogram from it. We can make a box plot from it. So histograms, box plots, stem and leaves. Now, the reason you wouldn't use a stem and leaf is because it's going to look ridiculous. That is the stem and leaf. Oh, it's going way off the screen. So there's more observations than it can show. We'll just do 100. And there's 100 observations in a stem and leaf. When you start to get so many observations, it goes way off the screen, and you just don't really want to do stem and leaves for very large data sets because you're going to see every single observation. You could do box plots, you could do histograms, but a histogram doesn't really give you a good idea if it's normal, because you might say, oh no, it's kind of got outliers over there. It looks like there's an outlier there, maybe some skew. Histograms are not the best way to view it. We want what is called a normal probability plot. And the way a normal probability plot works is you're matching up what you would expect if normal down here, -3 with -3 right there, -2 with -2. And this is where the line goes. So the values we observe are the dots, the black dots right there. And if they follow the normal, they'll follow the red line. Now, the red line is kind of a perfect normal, and nothing's perfect. I did generate this from random normal data, so it should be pretty normal because it was meant to be normal. But you see some deviations over here, a little deviation down there, and it follows the normal pretty well up here. Now, if it doesn't follow the normal, you're probably doing something that is skewed. And if you look at this, this is heavily skewed, right skewed data. You can see it in the box plot too with the high outliers. And the stem and leaf's also going to show it because the stem and leaf is just like the histogram, but is going to show the actual numbers. Like if you look at the way this is 0.1, 0.1. These are all observations. Make sure to review stem and leaves to know how to read that graphic right there. And that would be a bad stem and leaf with all those numbers. And you can see the high observation over here, which is 6.3 something, and the 5.9 right there. There we are. Now, if we look at the normal probability plot, the normal probability plot is way, way skewed. And there's a way to tell if it's skewed, because I think it's going to ask that for this one, if it's skewed. So if we want to know if these are skewed, a way to think about it, there's a few ways, is I like to think about people say it looks like an alien over here. So there's this person over here, and they are blowing it this way to the right. So that is right skewed. And that's because we see observed values that are extremely high. So if you go here to the observed values are much higher than we would have expected. This value right here specifically, we observe it at 6, and we would expect it around 4. So when you think about values that are too high, that is a right skewed data set. So values being too high, right skewed data right there. So that's why this is going to be right skew. If we had left skew, let's go here and times this by -1. Now this is left skew. You can see right here, it's kind of pushed to the left. If you do the same sort of trick I like to use and draw your little guy, he'd be over here on the other side of the graphic, blowing it to the left. You'd see because it's got that little push to the left right here. And also you can think about the same concepts with the deeper understanding of this, where the values we observe right here, we observe something at -6, and we would have expected this value right here. Well, that one's about at -4 or so, but we would have expected to see that at about -4, but it's observed, so it's much lower than we would have expected. And so if things are lower than we expect them to be, we're seeing some left skew right here. What software is this? This is R. This is R. I think it's a lot better for generating data. We can also do this in Jump. So if we have data right here, we could take and do analyze distribution and get the distribution of Y and do the normal probability plot here with normal quantile plot. And that will give us, oh, and look, that looks very normal because it follows the red line. So the more normal it is, the more it follows the red line right there. So this data right here, although the histogram makes it look a little weird, is following the normal pretty well. And that's the big concept behind a normal probability plot. The normal probability plot, when we take a look at them right here, this one follows the normal pretty well, except for a few outliers down here. And this one actually has the second modal distribution, and there is some weird skewness to it. So this one does not follow the normal as well. So the normal probability plot on the left shows all the data. Plot on the right shows it with the data set removed. This data set removed down here, so it's going to be just the peak more. What do these plots tell you about the shapes of distributions? The shape of the distribution with the Milwaukee schools removed is more approximately normal. And that's what we're looking at right. We'll go back to it. It's going to delete the question on me. Oh, it did. This is more approximately normal. And it's because it follows the red line. I mean, the line down the center. I wish they drew the line on it. A lot of software will draw a line through it. So that's usually a good thing to have, is your line showing you what the normal generally looks like. Any questions about this, Caitlin? Oops, still zoomed in right there. But the more it follows the line, the more normal it is. The less it follows the line, the less normal it is. That's kind of the surface level understanding of it. So this is pretty normal right here. And if you look at the histogram, it's also going to do it. Yep. And then definitely review the notes from class, chapter 5 right here, where we talked about the 3 ways to tell if it's normal. We didn't do a goodness of fit test on this, but the goodness of fit test, if we had done it, and this is normal data, the goodness of fit test would come back with a high p-value. And there's the high p-value. We can see the same thing over here in JUMP if we did a goodness of fit test on this data. And this data looks pretty normal. So if we go over here and do a goodness of fit test on it, the p-value should be high. Yep, very high p-value. The p-value right here is 0.995, which is about as high as it gets. And if you look, it follows it super well. It's basically on the red line. So this is about as normal as it gets. So yeah, looking super normal, following the red line. Very good right there. Okay, what else do we have? What other questions are people wondering about? Let me know. That is the first question right there, and a really good in-depth review of normal probability plots, knowing how to look at them and what they mean. What other questions are there? What other questions? Let's see here. I'll message stats 1. Might talk some BAS 320. But if you have questions, let me know. Let's see. Let's go over here. Let's check it out. Okay, for BAS 320, the Virginia, yeah, here, let's grab that right here. We'll do that here next. And draw more questions. I've got that next. We'll talk like 5 minutes on BAS 320 here real quick. So for BAS 320, we are doing associations between quantitative Y's and categorical X's. Is that from the homework or the quiz? That's from the homework, is it, Shana? We'll do that here next. I think that's homework, right? And so with this, if we were doing a quantitative Y and categorical X, nice. So let's check this out here for BAS 320. And you'll be using your Kaggle data sets. So if you have problems with your Kaggle data, let me know. But with BAS 320, we need to know how to use the associate function from library reg class. So let's load up a little bit of data right here. Hey, Jesse, good to see you here. And so right here, we'll throw some points to the class. We're going to go to associate. And this is a really great function. I think this one's super easy to figure out what it's doing once you take a look at the data. Zoom out a little bit here and redo the data. Okay, so what in the world do you think? So we analyzed, maybe people know in the chat, we analyzed, this is the Y variable of interest, this is the X. So we're looking at people's heights by gender. what do you think this is right here? What do you think this value, that 71.3 is? That value is right there. And this is a really good review of 201 also. You'll see it'll start to coincide here in a moment where you're like, oh, wait a minute. We were doing the same sort of thing in 201. Hey, Kaya, good to see you here. Haven't seen you in a while, Kaya. What is that 71? Let's throw points for Kaya being here. What is that 71.3? I'm a little under the weather, sorry. What is that 71.3? Does anyone know? I'll say what it is in a moment. Aw, we're doing coding right now. You can ask questions about anything. I might be able to help. We only got one more question after this. So ask questions if you want. That 71.3 is the average. See how it's on average for males. So that's the average height of a male from this survey data. 64.86 is the average height of females. The medians is also kind of important. We don't use mean ranks that much. Ranks is when you put the shortest person as 1 and the tallest person as, if there's like 699, the tallest person would have a rank of 699. So we're looking at the average rank, like if you ranked everybody from shortest to tallest. We don't really do much with that. I got promoted. Oh yeah, we could do for loops. Talk about for loops here. Yeah, we'll talk about for loops. I got that on the docket next here. Okay, you got it. After we're doing a 2-1 after this. So we are talking, can we explain height using gender? So we could also compare medians. Now, a very important thing we talk about a lot in 320 is the practical significance. And the practical significance right here is the difference between medians. That's a very important thing to know. We might compare medians. We might not compare medians. Sloan, good to see you here. We'll do that next. Well, thank you. And Sloan and everyone, and Kaya might remember, how would we know to compare means or medians for this graphic? So think about with 201, because now we're into like a 201 crossover topic. When would we compare means? When would we compare medians? This is a 201 topic now. When would we compare means? When would we compare medians? This is, if you're in 201, this is very good right here. Depending on the shape of the distribution, right? That Kaya, that's exactly right, right? So that's 201, right? We need to know if it's normal or skewed. What is the number one way to know if it's normal or skewed? What is, and literally that, oh, I'm going to Photoshop. What is the number one way to know if it's normal or skewed? What is the number one way to know if it's normal or skewed? The absolute best way to know if it's normal or skewed is going to be to make a what? The best way, we were just doing this question over here, the best way to know if it's normal or skewed, if it falls, and look down here, Sloan, you see this looks pretty normal. You could peek at the histogram for a moment. Sloan, you're exactly right. Does it follow the red line? This pretty much does. You see how this has deviations down here, and you can see it on the low side, how these kind of, this little bump right there. Yeah, manufacturing rivet. Put that right here after the next one. You guys, Jesse. So there are deviations from the normality. There are deviations. Are they really big? I would say no. And since they're not that big, I would note that. And I would say I'm going to compare the means. So to compare practical significance right here, I would say the average male is, and I can just take the numbers. That's what's so great. You don't have to do it yourself. The average male, we'll put it up here. On average, males are 6.44 inches taller than females. That's a half a foot. That's a big practical significance. And this difference is basically impossible by random chance because we look down at the simulation below, and via the simulated results, these are the differences we would expect due to random chance via random permutations. It's a longer topic if you're in 320. We review that and we talk about what that is, how we do the random permutations. And then here's our discrepancy way over here. None of the random permutations were as large or larger than ours, leading to a p-value of 0. Down here, we also say that we are very confident that the p-value is probably around 0 because we're 95% confident the p-value is somewhere between 0 to 0.007. If I was talking to people, I would say, like, I'm very sure of these results. We ran a simulation to tell us that the p-value is definitely statistically significant. So that's what I would say about that, because all you're trying to figure out is 0.05 in the range. Is this statistically significant? This up here, you're testing it by creating an interval of values you think might be true. And basically, we've interpreted the full output. There were 313 males, 386 females, and then just tells you gender is categorical, height is numeric, quantitative, 699 complete cases, how many data values we have. The discrepancy is an F statistic saying that the differences between males and females is 756 times larger than we would have expected due to random chance. It's not going to be so important in our reports, but that's the majority of the output, other than talking about logging your variables and stuff down here with advice. So know your output, know every single number in here. Probably this line or these values are the least important to know, but the discrepancy is a standardized way to look at the differences. Jesse's getting those apps going right there. All right, let's head back over. That was 5 minutes, 320. 320, you're always welcome to be here. I'm like, where's my 320 at? Where's my 320? Okay. Jesse was wondering about the Virginia Company extension. Let's see. Here it is, the Virginia Company extension. And let's take a note. Cough drop right there. Okay, let's go do it. Here we go. Okay, Taylor's got one too. The mean household income. Okay, let's take a look at it here in a moment. Is that from the homework or the quiz, Taylor? Is that the homework or the quiz? Okay. So what you want to do for these is you want to draw them out. You want to draw these questions out right here. I'm trying to think. 170? 170, right? I do the math in my head. 170. 2.1. No. Okay. Not the real answer right here. Chapter part 2 homework. Cool. So we need to go over to the apps right here. I'm going to pin it in the chat. Someone's already, thank you, Taylor, Jesse, who already put it in the chat right there. So I was taking some educated guesses on those. We need to go over to the apps right here. And we're going to go over to the normal app right here. We're going to put in first our what and our what. What should we put in to solve these questions to start? And we could draw this out. I was trying to z-score it in my head. So what should we put in to start on the normal app? The mean and standard deviation. Exactly. So we're going to go right here and enter in the mean and standard deviation. The mean is going to be 1152. Standard deviation is 84. And that's going to draw the curve for us down below. So you can see the curve down here now has the proper values of the mean and standard deviation. Shanna, great work too. Excellent job. Let's throw some points. And now all we have to do, if it wants the percent above that weight, we have to change this right here to a probability, a p-value from x. And we're going to go here to where it says above, because it's saying what percent of steers weigh over this. And how close was I? So we're going to go, we can even round this, which is really nice. We can round it to 3 decimals. And the answer is it exactly 2%? Oh my gosh. What did I answer? Whoa. I just bounced around the answer. Did you see that? I answered 1.8 and 2.2. I should just averaged my 2 guesses. I was like, 1.8, 2.2. I should have just averaged my guesses. Yes, that's you can take some pretty good educated guesses of it. What I was noticing is when I did this, I found the z-score for it, or I estimated the z-score in my head, observation minus mean over standard deviation. So the z-score is about 2. So if you go to the normal model, and this is not how to solve these questions, but if you were to go to the normal model, which we could draw out right here, we have a drawing right here, and above 2 is 2.5. Does that make sense? So if you look at this curve right here, we landed, I'm going to remove a lot of stuff on here. We landed where that green line is. Because if you z-score it, we landed all the way over there. And also take a look at your graphic. So it's not quite 2.5%. That's 2.5% above there. We landed a little bit further to the right via the z-score of 2.6. And if you look at your graphic right here, your graphic should look a lot like that. So if we put these two side by side, you'll see that our little drawing right here. Does that make sense? Like you have this right here, but this is, we're a little further to the right of it. We're at 2%. So it looks kind of similar to what you get right here. And that's how I was able to take that educated guess. So I can take a lot of educated guesses. This one's tougher though, because this one is a z-score of about 1.5. Here, I'll do one where I don't know the z-score and it wants under 1.5 is like 90. This is very hard to guess. 93.1. No, it's going to be a decent guess, but I'm going to z-score it right now. Observation right here, observation minus mean. That's observation minus mean. Let's write that down so people can see. To find the z-score at any time, we have to do the following. Observation minus mean over standard deviation equals z-score. So if I observe a steer wing 1275 and the mean of the distribution is 1,152, that's the difference, over 84. Now we can do this right here. There's the difference, divide by 84. I said it was about 1.5, it's 1.46. That means if you go back to the curve we drew, where's our curve right here? So we're at 1.46. And this is not how to solve these questions. This is the deeper understanding, which we try to go for. I'll show how to get the answer exactly. We are right about here. That means if we use the empirical rule, the answer has to be between 97.5 and 84%. 84% because 16% is above here, and that's because 32% is outside. But does that make sense? This is more like a test question right here that asks you to use the empirical rule, where your answer has to be between these numbers. And it's probably closer to 84%. No, it loses area, it gains area faster. It's going to be pretty close between those. You can't just average them, though, because you can't just say, well, it's between, because these areas are not symmetric right here. So you can't just take half of the 13.5 that's between there. So that's using the empirical rule, which the question does not have us do, but we can take educated guesses. And we'll go a little bit higher right here to this. And we didn't get it. But it's good to see if you're close. If you're close, you understand what's going on. Because all we need to do now is take the value we were looking at, the 1275, put 1275, and go below. Now, and so it's 92.8. So does this picture right here look a lot, and this is the key to solving these problems, understanding them, does that picture right there look a lot like our drawing right here? What do you think? This drawing over here, if we were to shade in the area, do those look pretty similar? And we said the area should be between this. So the answer is 92.8. That's the deeper understanding where you're able to draw it and say, okay, so what would this look like? How would this be on the curve? And if you notice here, this has the z-scores. This has the actual numbers. You could have entered in the z-score too. So another alternative solve is to go here, put a mean of 0, standard deviation of 1, and then take the z-score you found right here, and you will get the exact same answer. So now it looks exactly, at least with the axes on it, we have the same z-scores. So you could do it by entering in z-scores and have the between 1 and 2. So a lot of good practice right there. So it was 92.8. What was our first guess? Man, we were close. These answers don't have much give on them, so you have to be careful right there. This one is super duper hard to get. Well, we're kind of lucky because this is very close to the mean. And what is the z-score for the other one? 97.5. That's below the mean. So that's the distance it is away divided by. We can take a pretty good guess at this. We can take a pretty good guess at this. I think I might be able to get it. Darn it. No, it's gonna, yeah, because it's, yeah, it's gonna lose a bit. Well, darn. So pretty good guess. We'll see how close we were. Because going back to our numbers here with the mean and standard deviation, enter in your mean and standard deviation, go to between, and we can enter in the numbers it gives us of 1150 and was it 975? I think it was. So there it is right there. If you notice, we're right here basically at the center. Then we're going down to almost to that point where we were before on the other side. So that's what I was kind of using to solve it in my head. So as long as I've entered the numbers in the right way, and there it is right there, 90. I think you can, on his applet, reverse it and it'll be fine. We'll just enter it in the same way as it is written, and we will have the same answer of 47.3. So pretty decent guesses again. And you want to be able to think about how the drawing would look. Does that make sense right there? Once again, if you were trying to do this question quickly, which, you know, I do suggest learning how to solve these and to draw them. That's the deeper understanding. You want to go right here, enter in your mean, enter in your standard deviation, enter in the value below. Make sure you're selecting this right here. And then go below and 1250. And there's the answer for the first one, 87.8. Oops. Does it have any give? No, it doesn't. Wow, look at that. You have to be exact. So wait a minute. What did we do? Oh, it wants above. So here's a trick. Since it wants above, it's going to be 12.2. I'll show you why. I didn't click above for this one. I clicked below. So if we know the data below is 87.8, then the above is minus 100. So I realized I clicked the wrong button right there, and that's very common. So make sure you understand these sorts of relationships, that if 87.8 is below this point, 12.2 is above that point. The next one asks below right here. So below 1200 is going to be 71.6. The next one asks between 1050 and 1125. Go to between 1050 and, what was it, 1175? Oops, I have a second one. 1125. 26.2. As long as you enter the numbers correctly. 26.2. Does it have any give? It does. It does. So that's a really good question right there, going over it. So does that make sense? And let's see right here. Kaya, are you still here? Kaya can do some for loops. Just have a yes in the chat if you're still here, Kaya. We'll do a little bit of for loops and we'll come back here and do more 201. But Kaya, are you still here in the chat? If not, I'll do it. I'll still do it, but I'll do it after we do a little more 201, because we'll do 201, 201, and then go to little 474 for loops. We'll see. Get the next question loaded up here, and if Kaya says yes, then we'll hop over to that. A company that manufactures rivets. A company that manufactures rivets. Which number is that? It looks to be a quiz question. Where is, someone said a company that, or is that chapter 1? The mean household income. Here we go. The mean household income. Little chill music. 35, 13, Stat 201, chapter 5, homework. Okay. So for this problem right here, we're basically doing the same sort of thing. So if we wanted to see if this value here, would ask the top 19% of incomes. Where would the top 19% of incomes be on the normal curve? On the normal curve, where would the top 19% of incomes be? Can you tell me a z-score that they would be close to? Where would the top 19% of incomes be? Once again, we always go for the deeper understanding on these problems. So the top 19% of incomes would be the what percentile? It's a good way of thinking about it. The top 19% of it'd be close to the 84th percentile, right? What specific percentile is the top 19% of incomes? The top 19% of incomes is very specifically the what percentile? Great answers, Jesse, right there. The top 19% of incomes is the 81st percentile, exactly. Because that means 81%. It's going to be over here somewhere. Does that make sense? This is the 81st percentile right here, somewhere in there. Not exactly, but we know it has to be between these numbers because of the 50th percentile and the 84th percentile. And this means 81% of incomes are below there. So let's go ahead and make this graphic for us. We have the app pinned on the screen. we're going to go back here and go to z-scores. Now I'm going to do two solves for this question. You need to have the p-value or x, there it goes. And we're going to go right here and say 81. And this is the z-score of the 81st percentile. So this is the z-score. This should work. I have another way of solving it that will just directly give you the answer. But what does this z-score mean right here? This is the z-score of the 81st percentile, which is where the top 19% is at. So the top 19%, which is the 81st percentile. If you remember our graphic we drew a second ago, do we still have that up here? So you want to look at your graphic and be like, that's what I said it would look like. And yeah, that's what it looks like. Yeah, looks the same to me. There's my graphic. And there it is right there. Looks the same as what I drew. So what does the z-score tell us? That the answer to the question is what? The answer to the question is what? These are sometimes how test questions are phrased. The weights of steers? Mm-hmm. What does this z-score tell us? Because I think these are where people usually get stuck on questions on the test. What does the z-score tell us? How could we use that to find the answer? Because we know where the answer is at now, right? The z-score tells us that the answer is 0.878 watts. So that's where the top 19% is. What does this z-score mean? That's the big learning objective. Where you're like, oh, if I know the z-score, then I could go back to here, and the answer is 8.78 standard deviations above the mean because I know the z-score of it. So how many? Great job, Jesse, right there. So the z-score we found was 0.878. So the answer is 8.78 standard deviations above the mean. So we need to go to the mean and then do plus the z-score times the standard deviation to get the observation. This is a reworking of the formula. Z-score equals observation minus mean over standard deviation. But this version of it is basically what a z-score is. It's how many standard deviations an observation is above or below the mean, because that's the z-score telling you that. So we need to take those values right here and plug in the mean. It says the mean was 89930 plus our z-score that we found times, next we have right here the standard deviation of 85,000. Now this might give me the right answer. The first Stat 201 exam. I think we did that. We can do that one here. We did it in a different office hours, but we can. Is that the one with Reginald and Sarah? Now, this might not be right, and I'll explain why. Don't do this. Let's see if it gives it to us here. It did. Okay, I'm very happy that worked. That's one way of solving it, but there's an easier way. The easier way, which is less learning, so I didn't do it that way first, is to go over here and put in your mean and standard deviation. So once again, you can have the applet just enter in for you the mean and standard deviation from the distribution. So the mean was 89930, and the standard deviation was 85. There you go. And now our number that we found, 164,560. Luckily, there is a plus or minus on this question, which I was hoping there was, because we could have carried way more decimals. Probably if we were being very exact, we would have, because there's way more decimals to carry. So, maybe it should say in the problem, carried this many decimals. I'm glad it gave it to us with 3 decimals being carried, but we could have entered in just the actual numbers, and then this number right here would work. Just to show you, well, here, we'll do it again, maybe. Hi, Brian. Martin, good to see you here. Which one is it? Martin? Quiz 1? We can check it out. Yeah, let me know, Martin. So what's the problem with this data? Well, if you look at the distribution, this is incomes. So what do you notice about the incomes of individuals? Incomes shouldn't usually be what? What do you notice if you draw the distribution of incomes right here? This is how much money people make at their job each year. Not like expenditure or net. This is how much money people make at their job each year. So if this is the distribution, what's the problem with it? Got like 200,000, 400,000, negative 200,000. Remember, these are incomes, right? So they shouldn't be negative. We shouldn't see negative. And so probably this data is skewed, and it's very exemplified by the mean being higher than the median. So if you look here at the mean of 89,000, if data is symmetric, where should the mean and the median be? If data is symmetric, where should the mean and the median be? If you have symmetric data like this, where do you generally see the mean and the median? If data is symmetric, where do you generally see the mean and the median? Yeah, we can do that one right there, Martin. Tell me the very start of the question. I think I know how that one goes. We can do it here. Where do you see the mean and the median? You would see them at the center, or if it's unimodal symmetric. So they'd be in the same spot, they would overlap. But if it's skewed, then the mean will follow the skew. So when you have something that is like right skewed, if you have the mean as that blue line, so you have data that looks like this, the mean will follow the skew and the median will be there below the skew. So the mean goes in the direction of the skew. So if this is right skewed, so skewed to the right, the mean will follow the skew. And that's what we see over here in the summary statistics they report. The summary statistics say that the mean was this. There's the mean, and the median was this. So the mean is going to the right. So this is right skewed. Glassdoor. Mm-hmm. Good deal. So it's possible, and we need to see right here, choose the correct answer. It's only possible to be confident in the answer for part A. Nope. It's only possible to be confident in the answer for part A if the distribution is normal. Where does it say normal? Is unimodal, here we go. It's only possible to be confident in the answer in part A if the distribution of incomes is unimodal symmetric without obvious outliers. That means normal. Mm-hmm. And right here, since the median is much less, no, in standard deviation, I don't care about that much. Since the median is much less than the mean, since the median is much less than the mean, it is likely that they have more. No, since the median is much less than the mean, and the standard deviation and the mean are very close together, well, it's right skewed. There we go. I guess you could also look at other metrics, but the big thing to me is that if your mean is higher than your median by a large amount, then that is, and you could look at the standard deviation to consider that a large amount, like that is about half a standard deviation. So you're seeing a big kind of right skew to this data. And it's important to know the concept that when the mean is higher than the median, you are seeing a right skew right there. And they're saying that this distance right here is about 1 standard deviation. So that's not negligible right there. That's a large standardized difference between the two values. Let's see the next one we have, a company that manufactures rivets. Which one is that on? Let's see. I think we got to go to the quiz right now. So let's go check out the quiz. Here we go. The quiz. See which questions we have. I think everyone used the normal model. Here we go. Use the normal model. First question we see. And then we got a chapter. Which one, Jesse, were you wondering about? High school seniors. Can you put the star of it, Martin? I think that's what people look for. And then Jesse has one too. Trying to find Jesse's question. Company manufacturer. Oh, in chapter 1 quiz. Okay, there it is. Oh wait, chapter 5. Okay, there's that one. Okay. check this out. Here we go. Glassdoor. Yep. We got that coming up here next. Got it on the docket. You got it. Okay. So for this question right here, where do we need to go? Who can put in the chat? Where do we need to go to solve these questions? Because this does not use the empirical rule. What percent of IQs are expected to be over 80? What should that be? Over 80. So over 80. I'm trying to think. I'm trying to solve it in my head. So that should be to the right of that. Should be out. Oh, we can't below 85. Oh, we can kind of get this one. Having a little fun. See how close we are on our answers. 112 to 128. We'll just take a quick guess on that. Sure. Okay. Is that for mine? So with this one right here, this is the IQ one. So what do you want to do to get a deeper understanding of this problem? If you want a deeper understanding of this problem, what should you do to start? What should you do to start? There's a few. We're going to solve this right here. We'll see how close my answers are. So what should we do to have a deeper understanding of this problem to make sure we understand how to solve it for the test? Because that's what we're working towards, is we're going to work towards the test on this and think about how to do it. Draw it out, Jesse. Exactly. Notice here the mean and standard deviation. So let's go over here to a new sheet of paper and draw it out. Perfect answer, Jesse, right there. That's what we're going to do. And so we draw on the curve. It really comes down to practice. It's like playing scales on a piano. You know how to draw the normal. The mean is at the center. The standard deviation is what you go up each time. And then, so there's the top. We're going to do each of the answers on here and see if we can take educated guesses on them like I was doing there previously. And so here we are. So there are all the numbers. Colin, good to see you. 50 points, Colin, there from Disney. We love it. So the first one was above 80. So greater than 80 was the first answer. So if you're wondering why I drew what I did, 80 is about over here. Maybe a little further. So 80 has to be definitely more than what percent? Using the empirical rule, if you go to 80, 80 is going to be above there. Think about this. What percent of area is between here and here? What percent of area have I drawn on the screen right there? What percent of area is on the screen? Drawn in the orange arrows. 68%. And if 68% is there, then 32% on the outside, 16% each arrow by dividing by 2, these 16% are not the same. So we know our answer has to be more than what right now? Because if you go across the arrows, that's a certain amount. The blue area has to be more than what? The blue area has to be more than what? The blue area has to be more than what? 84%, exactly. So that's why I took my guess. I just took a guess right here, and I said 89.6. That's how I took my guess. I said, it's got to be more than 84%. Okay, so I'm taking a guess. The next one says below 85. Now, this is where, and I might update my guess, think about below 85. Is a good one to guess right here. If we go to less than 85, well, 85 is right here. And that has to be a little bit bigger than what percent? We can use the same trick we did a moment ago and think this has to be, so Jesse, try to answer this here while I draw it. This has to be a little bit more than what percent? I'll see if I did it right. Well, giving hints right there. Using the empirical rule, this has to be a little bit more than what percent? A little bit more than 16. So that's why I took my guess right here. Let's see what my guess was again. I said, ooh, see, I did it wrong. So we got to update the guess, 17.8. We'll go to 18.2. So that's my guess right there. I did it wrong, so my guess is now better. And then this says between 112 to 128. And we're basically just doing what the applet does for us. 112 to 128 right here. So when we go from 112 to 128, we're going right here to 112, which is a z-score of 0.75. And 128. I know this area right here. This area is 13.5. But that area over there is bigger. So it's got to be bigger than 13.5. This is a very hard one to guess because you're drawing this right here. So it's got to be more than 13.5 if you were to shift it over. So I'm going to go like 16.8. We got 0. Okay, so now let's get the real answers. To get the real answers, we need to go to the app. Make sure to go to the apps on the screen right here. MuBot's got it at the top of the chat. Go to the apps that MuBot is showing, and we need to put in the values. So we're going to go right here, put in the values right there. Make sure to click this one, and then we'll zoom out a little bit here. We're going to plug in the mean of 100, the standard deviation of 16, and it just drew the curve for us like we drew right there. So it's drawing the exact same curve we have on the, whoa, what did I do? 116. It's drawing the exact same curve down here that we saw previously. So make sure to get the curve drawn. And then we say over 80, above, and we need to go to the second one right here, above 80. And to 2 decimals, or how many did it want? It wants to 1 decimal place as needed. It's actually 89 on the dot. We were pretty close, but not within the margin of error. The next one says below 85. And when we go here to below 85, it's going to look just like our picture we drew. And the answer is 18%. So remember, it's just drawing the picture for us and getting the answer. And this is what we drew and estimated. And we said it was a little more than 16, but the exact answer is 18%. And we are doing it to 1 decimal, I believe. Remember, this does give you the option to round up. So let's see, above 80. Make sure we were rounding. Ooh, see, we didn't round. Make sure to round. So you need the 3 decimals selected right there, 88.7. Might have got it wrong if we didn't do that. And next, we are going below 85. And 3 decimals, 18.2. That is below. Below, above, those look correct. Make sure. That is below, exactly. And then between, right here, 112, 128. And that's 18.9. So pretty good guesses. And we should get everything correct if we entered in. Wait, what? What did I do? What did I do? 116. Right now I feel like something's wrong with the question. Do you see it? Do you see the problem? What is the problem? 100 points, first person to see the problem. I don't know how I did that. Exactly. Boom. User error. So there it is right there. Yep. I was like, what's wrong? Above 80. 89.4. User error. That can happen. That's what we do. It's a little thing like that you don't catch. Below 85, 17.4. And next but not least, or next and least, 112 and 128, 18.7. Really, so that's so close. Wow. There we go. If we didn't get it right, then I'd be like, what? So once again, really the deeper understanding comes when you draw these out, because you want to understand what you're doing right here, where you can guesstimate the percentages and how it would look on the normal curve when you do something like, let's say below right there, we're doing below 85. 85 would be above 84, so it's a little bit more than 16. And remember, that's what we found for this problem right here. The answer was 17.4. So this area right here is 17.4. The other one we did before that, which we had a really good estimate of, let's go back to that one. So we did also the area greater than 80. And we said it had to be this big area right here. So that area mathematically turned out to be 89.4. And then we can also do the real drawing of it over here, where we say above and go to 80. And then once again, you could check your work here to be like, okay, does this graphic I drew right here look like this graphic all the way down here? And then you say, okay, did I do a good job drawing this? And I think a lot of times people don't want to do these extra drawings, but it really helps to ensure that you understand what you're doing. So video of class sources. Yeah. How do you get to the class videos? How do you get to the class videos? How do you go back and watch class? So I'll answer that right here. How do you go back and watch class? So if you missed something on Monday, how do you go back and watch class? How do you do that for 50 points? Where do you go? And then we got another question right here. Good practice, the Glassdoor. We'll go find the Glassdoor one. How do we go and watch class? On Canvas. Where on Canvas? Good answers, Jesse, right there. On Canvas, you want to go to the, I'll find it right here. I'll show you. On Canvas. So under Canvas, you want to go to the Watch Class Live. So they're not posted to YouTube. So the reason is your classes are unlisted links. So if you go here to the Watch Class Live, I'm not going to click through this. This will bring you to the playlist. You can also go to the announcements, but the classes are not viewable on public YouTube. So that way there's not like a random person who comes into the YouTube chat and says things. Yeah, so that's what I do. Once again, you don't have to use your real name, but rather than anyone on YouTube being able to find it, I mean, it's kind of like if someone shared the Zoom link for the class. Like I can't stop someone from being like, hey, here's my Zoom link for the class, join my Zoom class. I can't stop someone from being like, hey, here's my YouTube link for my YouTube class. But it's unlisted. The office hours are public. The classes are unlisted. And then I don't click this because then it would show the URL. I don't know if anyone would take the time to type out the URL to get to the playlist, but it would show the URL for the playlist. But Watch Class brings you to the playlist with all the classes. Good questions right there. That's a big thing to know. 100 points for asking Caroline. Maybe someone else was wondering that too, but that's how to get to the Watch Class right there. Just click Watch Class. Yeah. No, that's what I want people to ask. That's why, if you ask, I'll tell, and that's the best way to know. So that's why I give 100 points, because now you can go back and review, which is really good. That's what we want. Let's do the Glassdoor one right here, and I think we've one more after this, and we're gonna do a little for loops. We have the accompanying manufacturing rivets from the first quiz. You're welcome, Caroline. And 59, 13. Stat 201, chapter 5, quiz part 2. Okay. So they're given some crazy percentages right here. Oh, but this one's easy. We got this. It says, what percent of CEOs, according to the normal model, would we expect to earn more than 2 standard deviations above the mean? So between +2 and -2 is what percent of the data? Between +2 and -2 is what percent of the data? We could use this one right here. Between +2 and -2 is what percent of the data? On the z-scores. We don't even need to know the context of the data. 95. So if 95% is between here, then what would we expect above that arrow right there specifically? So you would say we want to find the outside portion. So the answer for this should be what? If we're talking about 2 standard deviations, the percent of area above 2 standard deviations would be what according to the empirical normal model? So it's having you basically use the empirical rule here. What should it be? So what is this arrow worth right here? 2.5. Great job. Yep. And you've got it right if you add up across the arrows and they add up to 100 because you've gone through the whole curve right there. So it is 2.5. There we go. 2.5. Yep. Is the percent appropriate for these data? Looks pretty normal. Okay. The middle 95. Do they give other things? The meanest standard deviation. Okay. So the mean is 1.07. And the standard deviation doesn't look. The histogram of log compensation is given with a mean of this and a standard deviation of this. Okay. Let's see. Okay, so let's look at the nose. The data is skewed. No, the data is not skewed. It's not uniform. Okay. It's probably going to be this right here. Yes, because it is unimodal and fairly symmetric. Hey, Kayla, good to see you here. Is that the homework or the quiz? Which one? Can you tell me the start of the question, Kayla? And then we'll check that out. Good to see you here. It does look mainly uniform and symmetric. Now, what they're doing, like, there's some little lack of symmetry right here. And then, oh yeah, we got this one right here. Can you put the start of the question, Martin? Like, what's the very first, like, 8 words in it? And then I'll put that on. I'll do that here next. So what they're doing right here is they're doing a transformation of the distribution, which will change the center and the scale of it. So if you notice right here, this distribution is scaled. Scale is the spread of the distribution. And if you notice right here, it goes from 0.1 to 2.1. The center is at 1.1. So they've changed it so that it has a new center. So that's shifting the distribution. And then they've scaled it to a different scale, doing a log transformation. Now let's draw samples of 30 CEOs from the logged. We draw 1,000 samples from there and found their means. The distribution of the means is given with a standard deviation of 0.05. Do you think the 68, 95, 99.7 rule applies? I mean, yes, it looks pretty unimodal and symmetric. Yeah, I mean, that's what we need. It can't just be unimodal because it could just be one mode that doesn't show the symmetry. So unimodal, we had a really good drawing of this. There it is right there. Oh, it's the one right above it, right? Oh, it's this one. So if you just have something that's unimodal, it could be skewed. So for the 68, 95, 99.7 rule to apply, we have to have unimodal and symmetric. So you could just have symmetric, but you could have things like bimodality or uniform. You could have things like unimodal, right skew, unimodal, left skew. So we want modality. Thank you so much. We'll put that here next. Thank you, Martin. And that helps me find the question a lot quicker. And then we got rivets too. I think they're both on the chapter 5 one. So with that. And so with this, we should be good with this. I think so. The first one it's asking about right here, I don't think it's saying that's skewed. It's definitely the first one. Hopefully I didn't misclick. The first one is definitely not uniform. That would be flat. That's not flat. The first one is definitely not skewed. I don't see any major pull in a direction. And then for the 68, 95, 99.7 rule to apply, to use it right here, because they're using the empirical rule for the normal model, we should be good. Yeah, I was second guessing everything. It's basically, does this look normal? Does this look normal? And they're using actually method 1 to check normality. Method 1 is look at the distribution and see if it looks normal. So that's kind of the key learning objective of this problem, is you can look at a histogram and think, does it look unimodal symmetric? And if it looks unimodal symmetric, you can use the empirical rule. So always think about what this question is trying to teach you, to think about the key learning objectives of, does this look normal? If it's normal, what would we expect above 2 standard deviations? And that is 2.5 according to the empirical rule. And then when do we say things are normal? Well, if you look at it and it looks unimodal symmetric, then we're pretty good right there. I mean, is it perfect? No, but does it mostly look? And that's what we go for. So when you look at the data right here, you want to see, does it look mostly normal or mostly not normal? Good stuff right there. I think we got some chapter 5, part 1 here with the high schooler uses and accompanying manufacturers rivets. Let's go check those out. Okay. These are the first set of problems. Let's go check out part 1 quiz. And then we have a homework question too, I think. Thank you, everybody, for being here. Okay. There's something wrong. Oh, no. So when you... good question there, Martin. When you go back and look at a quiz, click the answer and it'll say you answered. So when you look at a quiz and if you get something wrong, click the answer it shows, because it's showing you the right answer. And then if you click the answer, it'll say you answered. Does that make sense? It'll change it to the right answer. And then it'll say you answered if you click on it. It'll show you your answer. It's a confusing thing. I wish it just said like, I wish I put an X instead, or put a thing next to it immediately and said like right answer. But a lot of people are confused on that a lot of times. They say, wait, it's changing the answer. Because at first I thought it did that to people, and then I realized it's just confusing the way it does it, that the right answer is shown to you, and when you click it, it says you answered. And then so click the little red box next to it. That's a very common question I've gotten. I'm always ready for it to start semester. So 50 points Martin right there. It's a good question to ask, which I wish they just made it. Maybe they could have a box that's on it normally, say like, you answered this, correct answer this. Like, that would be better. You're not the first student to get confused by that. Because, I've had students being like, I swear it's changing my answer. And I'd be like, just click on it. It's a good question right there. All right, here we go. Let's check it out. High school senior. So this question's really good about the center and spread of distributions. So when you think about this right here, let me take the note on the time on it. 107:53. Stat Tool 1, Chapter 5, Quiz Part 1. Okay. So it's important to know what measures here are center and what measures are spread. So which measures, and center is a measure of position. So let's first say what measures here are measures of center. So these are very important things to know. What measures are measures of center right here? So first question I have for you are what measures on the screen are measures of center? Median and mean. Jesse, you're on fire. You got those answers. What measures are measure of spread? What measures here are measures of spread? What measures are measures of spread? Those are the main two we use, and there's a third on the screen. There's a third on the screen. The third, you can use it, use all the time, yeah. Range, and then we know that median is paired with IQR, standard deviation is paired with mean. Now, max is interesting. When it comes to max temperature, think about how median, think of a P word, is a what 50th something in the data. When you think about the median is a what in the data. It's right here. Yeah, Martin, good job right there. It's a percentile. So the median, and just like Q1 and Q3 and the max are all percentiles. So it's like a position, right? Does that make sense? It's like a position. And let's think about, so it kind of is more like the position of the max, the position of the mean, where the range is a spread of things. It measures a distance two things are away. Standard deviation measures distance things are away from the mean. IQR measures the distance between Q1 and Q3. So let's think about this. If I had test grades here, you ready? Here's test grades. I have a 70, 75, and let's go. We only need this. Okay. So I say everyone gets 10 points because the highest grade was a 90. So if everyone got 10 points, so I'm going to go plus 10, I am whatting the distribution, shifting or scaling it. Plus 10, would that shift or scale it? And by shift, we mean move the center of it. So if you're wondering what shifting looks like visually, shifting a distribution looks like this right there. Jesse, you're on fire. Shifting looks like this, where we're moving the center of it. Scaling changes the spread and changes how far apart the numbers are. So this is scaling it. The center's still in the same spot. And this is shifting it left and right. So I'm basically shifting it to a higher position. So when you shift data, what about this changed? If I shift the data, let's start here at the beginning. Did the maximum change? If you shift the data, did the maximum change? If you shift the data, oh, no worries, Kaya. Yeah. We'll do it here soon. The max did change. You can see that down there in the bottom. Did the median change? If you shift the data, I think, well, Jesse, you're following. So I'm going to answer questions too. The mean did change. Did the range change? The range is still 20. So it looks to me like shifting data does not change the what. And we could calculate each of these, but shifting data does not change how what out the data is. And you can see it if we look at it. Shifting data does not change how think of the S word, how spread out the data is. So if you shift data, it's not changing the spread of the distribution. I have to enter these in the grade book out of 10 now. So I'm going to divide, I'm going to take your grades and divide them by 10. So now we're dividing these by 10. So this person got an 8. This person got an 8.5. This person got a 10. So now we have scaled the data. Does this scale make sense that they're less spread out now? I mean, that's what scaling it will do. So think about this. This is really interesting right here. And this will literally be how we can answer the question here in a second. So now that we've scaled the data, did that change the maximum? Is there a different maximum now? Like the maximum was 100. Has the max changed? Yes. And if I average these, they're going to have a different average. We're not going to get a higher 80s average. What is the range of the data currently? What is the range of the data currently? The new range down here at the bottom. The range, which is the max minus the min, it's 2. Yep. So what are you noticing scaling the data does? Scaling the data, I did divide by 10. Yeah, that's good. Scaling the data did what? It changed what? Scaling the data can often do what? It changes the center and the spread. Yep. And there's ways to do it without changing the center. Like if everything's z-scores, then it wouldn't change the center because it wouldn't change the center because center would still be 0. Well, yeah, 0 times something is still 0, right? So I guess technically you're still multiplying by it, but just 0 because 0 is the center of the z-scores. So really good stuff right here. We see what it changes. So this is the answer key to how to do it. Yeah, I know. The chefs opened their own in Farragut. Thank you. What's it called, Kaya? We're going to go there as soon as we get back to Knoxville. Pantai? Okay, well, check out Pantai. I'm going to give them huge shout-outs. I support the owner who I read on Reddit was just getting older and tired and wanted to take time to herself, it sounded like. But I support her doing that. She was really kind to me throughout many years of going to Taste of Thai. So huge shouts to them. So the spread, let's do the measures of spread first, because spread is only going to get impacted by the whatting of the data. They're in Thailand? Whoa, so they went to, that's cool. Shouts to them. Surprise, I want to go home. Taste Thai is as official as it gets. And maybe she's letting them use the same recipes. I guess they are. So yeah, I'm going to Pantai as soon as we get there, get some pad ki mal. Yeah, I support her in her decision to say, I've done this for a while and I want to go home. I wish I could have saw her one more time and said thank you. She gave me like gift certificates one time during Christmas and was like, she put them on the table. She goes, don't tell anybody. I'm like, what is this? I opened up, it's like $20 gift certificate. I would seriously go there like every day. Yeah, they are a lot to manage, and they built their own restaurant. Yeah, such a good place. So if we look at our cheat sheet right here, the measures of spread will only change by scaling. Does that make sense? We wrote a cheat sheet right here. The measures of spread will only change by scaling. Does that make sense? The measures of spread only change by scaling. So the bottom 3 are measures of spread. So we're just going to take the IQR. The IQR was 14. And we're going to times the IQR by 1.8. There we go. This should be correct. I'm doing it a little quicker than I like, but the standard deviation is only going to change by scaling. The reason I'm timesing by 1.8 is because that's 1.8 right there. So we're going to times that by 1.8. The range is only going to change by scaling. So 30 times 1.8. And then all these measures up here. No. Because remember, the shifting, and good questions, Jesse. What we learned from our example right here is that shifting does not impact the measures of spread. Do you remember with the first thing right here? We won't add 32 to those because shifting does not impact the measures of spread. So when you shift data, it doesn't impact the measures of spread. We put the orange X's right there because when we added 10 to this, did the range change? Do you see the range was 20 here? And then when we added 10, did the range get 10 bigger? So do you see right here, it was 20 for range. 70 to 90 is a range of 20. And then is the range 30 now when we added 10 to it? Does that make sense, Jesse? So shifting data does not change the spread of a data set. Let me know if you have questions. Shifting data will not change the spread. So we don't want to add the values to that because it's not going to... Well, so if you were to convert a value, it would have to go through that formula. But the spread... So what is the spread of 70, 75, 90? What is the spread of 70, 75, 90? So what is the spread of 70, 75, 90? And then we added 10 to everybody's scores, right? And now if you take someone's score, you'd have to add 10 to it to find their new score. But think about this. The lowest went up by 10, the highest went up by 10. So if they both go up by 10, they're still the same distance. Does that make sense if I do this? Like, you're the lowest, this other person's the highest, or we'll say they're the lowest, you're the highest, and then everyone goes up by 10, you're still the same distance away, because it's kind of like cancels out mathematically. If you think about it mathematically, like you have here, so I could draw it more mathematical for those who want to see kind of the proof of it. It'd be min minus, or max minus min, max minus min, and then if we have max plus 10 minus min plus 10. Does that make more sense, Jesse, right here? So if you add 10 to both of them, well, then you're just going to be subtracting off these 10s from each other, and it's still just the two values. So that's kind of the mathematical proof of it, that when you do that, that doesn't change the range of the data. So adding 10 to the max and the min will just kind of shift the max and the min over a little bit. The range of them does not change because you would have the min 10 higher and the max 10 higher. They're still the same distance away. And if you kind of just think about it as 10 minus 10, that part of the equation right there is just going to be nothing. So shifting data does not... Does that make sense? I want people to have the deeper understanding, not just to plug the numbers in and solve it. But shifting data does not change the spread. So when I was doing the conversions right here, I only changed the spread. Yeah, I know this is a tougher problem, right? So when I did the conversions, I only did the conversions on the spread due to the whatting. So when I was converting the data and converting these metrics, I only converted on the what for the spreads. That's the shift, and that's the scale. So when I was doing the spread, and, or well, yeah, sure, center. It's gonna be chapter 5. Oh, Kayla, great work right there. So when you change like the measure of center, it's going to be hit by the shifting and scaling of it. And that's what we see in our example right here. So when we did the measure of center changing of the data, or when we looked at the measure of center, the measure of center is now 8.5, and that was hit by... Yeah, so hopefully it's making sense right here that this is where we scaled the data right here. So this was a scaling. I'll write that on here. This was a shift. And this was a scale. So the scaling impacted everything, and the shifting only impacted these right here, like the maximum change via shifting, the median change via shifting, but the range did not change, and other values like the IQR and standard deviation would also not change. We could calculate this to show it really quickly. Just go over here and go to scores, and go to 70, 85, 90, and then scores 10. Go to scores plus 10, and then go to standard deviation of scores, and standard deviation of scores plus 10, and they are the same. So there's ways to check it mathematically, but the scores we would not see, and we could do IQR also, like IQR. So I love code. You can just be like, here we go. There's the IQR. So the IQR did not change, but if we do scores 10 and divide them by 10, then we will see the IQR is different right there, and the IQR gets divided by 10. So this is once again kind of checking it really quickly with code to see that it is working. So we should get the right answers, is what I'm saying. So this has to actually go through the formula. The maximum is going to change. It's a position, kind of like the median we talked about. So if you were the highest score, you would be multiplied and divided. So we go right here. We plug 11 in, times it by 1.8, and add to it 32. And then the mean, we go to the mean. The mean's going to have the same sort of formula done to it. The mean was -1. That should be all right, right? Yeah. Yeah, it's just a conversion. So 1 negative times 1.8 plus 32 should be right. And then the median is -2 times 1.8. There we go. Yay! Good question, tricky. But we do have the cheat sheet over here, and understanding what shifting and scaling are. The most common shifting and scaling for 100 points is to turn data into what? The most common shifting and scaling. You're welcome, Martin. It's a tricky question. The most common shifting and scaling of data is to turn it into what? We do this a lot right here. The most common shifting and scaling. So you can see it right here. The most common shifting and scaling is to turn data into what? Z-scores right there. Yeah, Kaya right there, 100 points for the class. So you've shifted the mean to 0, and you've scaled the standard deviation to 1. So you can see the shift of the center of the data and the scaling. Once again, to see what shifting and scaling looks like, and shout out to Adam Spanbauer who made this. If we were to shift this over to 0, you would literally see me doing this right here. Ooh, so you see it moving towards 0. So this is shifting the center of the distribution over here. So we're moving the center. And now we've shifted the center to 0. That's shifted to 0. And then we'd scale it down to you see the standard deviation is getting smaller. So this is scaling it right here, decreasing the spread of the distribution. So once again, showing that scaling changes the spread of the data. We're making it more spread out. We're making it less spread out. And shifting changes the positions, like the maximum would be higher right here. We're moving the percentiles. We're moving them down now. Also the mean. So it changes positions right there. Really good way to kind of think about and show it. And that these are the notes once again we have for it. Just understanding measures of like center. Also, the maximum is a percentile, the 100th percentile, just like the median. So it's going to follow the same sort of rules that the median would change by. Yeah, good stuff. Good problem. And we have another one. And then Kaya's waited so patiently. Let's see. Kaya asked this a long time ago. Let's do for loops here, Kaya. So thank you so much, Kaya. Been here a while, asked about for loops. Let's do it. Okay, for loops. Yeah, that's what I appreciate, Kaya. And I hope, I know we hop over to R sometimes, and I hope people have an understanding. I'm gonna mark this 32474 for loops. Like do you still use z-scores? And get ready when you do clustering, or I don't know if you're on clustering yet. Do you still use z-scores in the upper level classes, Kaya? Do you still use z-scores, which is the standardized difference based on how many standard deviations something is a problem? We are getting to clustering. We'll get ready in clustering. You will z-score things in clustering. And then people will be like, wait, how do we turn that into a z-score? Observation minus mean over standard deviation. So the concepts you learn in the classes throughout business analytics or statistics are going to come into play multiple times. Now, a for loop has 3 major components. So if you're watching this right now, you want to know about a for loop. For loop has 3 major components. So the first component is the vector. Then we have the, oh my gosh, why can I not think? The variable. Cheating. And then the skeleton. Okay. I thought, yeah, well, yeah, that's what we do. because you could scale it to like 0 to 100 and just put it to like a percent scale where the min is 0 and the max is 100. What you do, scale data, shift or center it and scale it, shift it around. Yeah, very important concepts that are used all throughout our discipline. So you have to know what each one of these things are and what they do, even if you can't remember one of the names off the top of your head. Now, the quickest way to get to for loop is to use what is called a snippet. So a snippet inside of R is basically some pre-written containers for you. So I like to say when we do functions, we do F is for friends who do stuff together, U is for you and me, N is for anywhere and anytime at all. When we want to make a function real easily, there you go. So a snippet is going to do a lot of the coding for you. Get the reference right there. And so I wouldn't try to write all this out. Usually you'll make errors. If you want a shiny snippet, you can actually go here and get a shiny snippet, and it does all that for you by you just typing shiny. So when you want to make a for loop, what will you type, Kaya? Yeah, we got that next, Jesse, you bet. And that's on the homework or the quiz, right? You got it, Jesse. And thank you, Jesse, so much. You've been here the whole time, too. Jesse, 100 points. We're doing that one next. What are you going to type, Kaya, to get your for loop? What are you going to type to get your for loop? FOR. That's it. So you type FOR. You got to be careful because someone's going to be like this. They're going to go right here and they're going to go FOR. Well, it highlighted differently, telling us it's something other than just an object. We're going to go here and go FOR, pause, and use the snippet. Okay. So now let's know what this is. Type 4. Somebody's going to do that. So we need to know what each one of these things are. Okay, so first off, the skeleton is inside you. This is the skeleton. The code that runs. The variable. Put that first. The placeholder for what the vector, placeholder for the current element of the vector. The vector. This is what everything is. So when we do a for loop here, we will first start out by thinking about what do we want to code. So maybe the hardest part of it is because we're doing the skeleton first. And a lot of times you write one instance. This is where people fail at writing for loops. If I want to make a for loop that, let's say, finds the average heights of males and females, or the average height, is about a car loan? Cool. You want to do it for one instance, like one day, one group. Like, let's say, find the average height of people by handedness using a for loop. Okay. So we're going to start by writing one instance. This is the skeleton we're working on. So this is how to do it. And let's talk about how to write the for loop. The one instance we're going to write is we're going to find the mean for one group. So here we go. We're going to pull up some data right here. Then we're going to go to data survey 10. It's not the for loop stuff. And here's our data set. We have handedness of individuals. So the first thing I want to think about right here is I want to find the average height of people by their handedness. Well, pretty much. So yeah. I think you're on the right track, Kaya. So we're going to do one instance. This is exactly it. You're on the right track. So now we're going to go right here and we're going to say, okay, I want to make a subset of survey 10 where handedness is equal to right-handed. So these are only right-handed people, right? These are only right-handed people. Let's call this sub then. Let's go here to the height. And now I have the mean of their height. Does that make sense? I now have the mean height of right-handed people. So we probably want to store this somewhere and say mean heights. And we'll store this right here to mean height of right-handed. You can store to a position. So if you think about how I would run this now, I could run this by going right here and changing this to left, right? Oop, I just overwrote it. I need to change both of these to left. Oh. Is that making sense right there, Kaya? So all I did was just take a subset of survey 10, handedness is equal to left, store into the vector mean height, which I created up there, store into position left, the mean of the subset I made. But here's where we get into the exact theory of making a for loop. Yeah, we could add up on a for. I think we did that. Did we do that? We'll double check here. No, we did that yesterday, I think. Sloan, I'll send you it. We might not have enough time, but because, yeah, we did check out Sloan. I'll send you it if so. Sloan, 100 points. We did a big coverage of it, I think, yesterday. Because it's a little longer of a thing, but we could maybe do a speed run of it. So here's the big part about this. Let's just call this selected hand. And let's say write. This is how to write better for loops. When I run this code now, oops, didn't change that. Ambidextrous. How do you spell ambidextrous? That's not right. That's not right. There's no way. No way I know how to spell ambidextrous. Yeah, I don't know how to spell ambidextrous. We're going to still get that error message one. Okay. There we go. We'll delete that later. Or we can just delete it by restarting the vector if we wanted. But this is now working. So with this, we have now created our skeleton. We actually went through and made sure the skeleton worked with everything, which is not required. And a lot of times as you get better at building for loops, you don't always do this. You want to get the skeleton to work on what? You want to get the skeleton to work on what? The first goal of your skeleton is to get it to work on what? So going back in time right here, this skeleton, well, when it had right there. Oh no, we don't. Oh, what? Can't go back in time too far. Get the skeleton to work on one instance. One instance. And then put in a placeholder. I'll go forward in time. So now we have a placeholder in our for loop. Does this make sense, Kaya, right here? We now have a placeholder in our for loop, and this is a working skeleton because the skeleton never changes. Awesome, Kaya. Yeah, this is, like, I feel like you have some background knowledge, so I didn't go from the most basic. So notice now, all we're going to do is take this and put it where the skeleton is. Will anything in our skeleton ever actually change when we run the code? Will anything in the skeleton actually change when we run the code? Will anything in the skeleton ever change when we run the code? Like, technically, will any of this code, like, change? The skeleton never changes. Then now what will change? What will change is the variable will go through the vector. So the variable will change, right? But the variable will always be called this. So this was the variable we created that will change. And then what vector will it go through? It'll go through the something of handedness. So what should we grab that it'll go through? Remember, I was doing it down below. So what should that vector go through every time the for loop runs? Every time the for loop runs, it will need to go through the what's. The what's of handedness. Every time the for loop runs, it will need to go through, well, not the heights. So remember what I was changing right here? It'll find the heights. You're on the right track, Kaya. And Kaya, great work. So it'll go through the what's of handedness. Look at the very bottom right there. Because I was using ambidextrous left and right. Those are the what's of handedness. Because I wanted to first do ambidextrous, then left, then right. So those are the what's. Look at the very bottom right there. The kind of types, the levels. So when my for loop runs, I could just go here and do this. I could say right, left, but why not just input the levels? Why not input this right here? And then guess what? It works. So this did all the work for us and did it individually by cycling through and changing it. The first time this runs, it input ambidextrous right here for selected hand and ran the code. The next time it ran, it input left-handed for selected hand and ran the code because it's doing a different level each time. To think about what a for loop does, we should be able to interpret a for loop. So what will this for loop do? Now be careful. I'm trying to trick you. What will this for loop do every time it runs? Like what is the skeleton doing? So we could talk about it very specifically. Like there's lots of ways to say this, but the skeleton, no matter what, if you don't even look at the code above, don't even look at this code up here, the skeleton is doing what? Every time the for loop is running, the skeleton is doing what? And what is hello? Hello, is hello a word? What is hello? We could say hello is the what? It's the variable. So the variable is going to change every time the for loop runs. So what will the for loop do the first time it runs? So to think about this, we should talk theoretically right here and understand that every time this runs, it's going to print the object hello, which is what the variable is. So when the for loop runs, the first thing it does is it says hello becomes, or it's capital hello. So yeah, let's do it right. The first time it runs, it says hello, left arrow 1, and then it says print hello. So what will be displayed on the screen? My handwriting is so bad. So when the for loop runs, it goes hello, save into 1, print hello. Yup. And then it's just going to do what? Loop back to the top, change it to 2. Does this make sense here, Kaya, that when you think about what the for loop is doing, it's just changing the element, it's changing the variable to a different element in the vector each time it runs. Like our for loop up here starts by saving what into selected hand. You can just type the first 3 letters. I don't know how to spell it either. The for loop right there starts by saving. And start by writing the one instance of it. That's what a lot of people, they don't usually, a lot of people just start by trying to write a for loop, and that's like, well, that doesn't work. So it starts by saving ambidextrous into selected hand, then it runs the code. So why not go down here and try to get it to work on one instance? So if you're thinking, okay, wait, I'm going to have this variable right here, selected hand. Like here, we'll do one more example. Then we'll do probably one of our last questions today. Like let's say we have a for loop. We want to find the sum of each column in a data set. So what would be a good thing to do if we have a data set like empty cars and we want to find the sum of each column in empty cars? What would be a good starting point to do one instance of the for loop? So it says use a for loop to find the sum of each column. What would be a good starting point? Well, so you're on the right track. So if we want to find the sum of every column doing one instance, how would we do one instance as like to make a skeleton right here? To make a skeleton. So think about this. We want to find the sum of each column, like of the first column, of the second, of the third, of the fourth, of the fifth, every column. We want to find the sum of each column and do this using a for loop, which there's quicker ways of doing it, but just good practice. Well, so if we want to do it for every column, doing one instance, we could do it what? You're on the right track. So if we, like, what code would we write? If we want to do it for every single column, we should write a code that does it for which column first to see if we can do it. So we want to do it for every column. So maybe do it for the which column first and see if we can get the sum of that column. Because we just want to do it for one instance to show like, okay, we're going to do it for this column. So let's do it for the first column, right? So let's go right here and find the sum of the first column. So to find the sum of the first column, we go to empty cars and we go to the first column right here. And there's the first column of data, rows, columns. And then we find the sum of the first column. Does that make sense? That is the sum of the first column. And think about this. Now what needs to change? Nice job right there, Sloan. So now what needs to change? Now we need to go through each column. We need to do it for different columns. Let's say sum of column. And this will be stored into the first sum of column. And when we do this right here, great job, Kai, right there. Lowercase s, it might have corrected it. Now we need to go through here and we need to say column. And let's change this right here. And we just now decided on our what, basically. What did I just do right there? Because I basically have my, I did the mistake. I have now basically decided my what right here. On line 46, I basically have my what. That's about it, I think. Line 46 will be my what in this code. What does line 46 look like? The variable, exactly. So we have our skeleton. And we need where we create a place to store into. We'll check it at the end right here. And then the variable is this. And then it needs to go from 1 through the number of columns in empty cars. And there it is. A study, we might have how is the standard deviation affected? I think we did one similar to that. Check out, we might not have enough time, Mackenzie. Check out, we did one right before this, and we went through talking about, it's very similar to this, I think. So this, it might be the exact same type of question. Moira, hey, good to see you, Moira. A few stats questions, ask them soon. We only got 16 more minutes, and we got 2 questions at least right here. A study was conducted. We've got only a little more time. Ask all those. So does that make sense, Kaya? And great work right there. I hope that gives you a better understanding of for loops. And thank you so much for being here asking. Tell people we did a review of for loops. We're going to do some rivets. Can you go over a while loop? Nicholas, we might have to do it next class or next office hours. While loops have a condition. The while loop runs while the condition is true. So if we say while 1 equals 1, print awesome, the while loop will run while the while is true. Oh, while what happened? What happened? While 1, oh, wait. While 1 equals 1. Do the while loops break? Do infinite loops now break? They might have done that. There, okay, why did it not do, oh, I just probably printed awesome. Okay, it's an infinite loop. I'm holding a session today. I want to review percentiles in the area, normal curve. Could you got to calculate each of those by hand? We would have to use the empirical rule or the applets. So here's the new applets, Moira, right here. Mubot's going to put it right there. And so if you want to do percentiles on the normal curve, you would have to use the empirical rule. Let me show that on the screen right here. So this is using the empirical rule, Moira. Then we're going to do the last 2 questions right here. So the percentiles go from low to high. You could estimate percentiles. Like if I told you, we'll do one quick question here. The test scores are normally distributed with a mean of 100 and a standard deviation of 20. You scored a 130. Your test score was between what and what percentile? That's a fair test question right there. You scored a 130. Your test score was between what and what percentile? So these are good questions to ask Moira right here, which would show knowledge of the empirical rule and also show knowledge of percentiles, that the higher percentiles are on the right side of the curve. Percentile means what is below you. So what would you have a student do to solve this? Probably the first thing I would have them do is find the what for 130, which you could also kind of see it right here. What would you do? Z-score, yep, Z-score, observation minus mean. over standard deviation. It's a z-score of 1.5. And so you can see it on the curve with the z-scores right there. And all of these numbers right here are obtainable using the 68, 95, 99.7. So if you're wondering why that's the 84th percentile, you'd want to go here and put 68 according to the empirical rule, and that leaves 32% outside. So if 32% is outside, 16% is here, and 16% is here. So that means this is the 84th percentile, and the same applies for the 95 with 95 in the middle, 5% outside. So you could do the same rule for this to know the percentile here, 95%, 2.5% above here. That makes this the 97.5th percentile. So you're somewhere between the 84th to 97.5th. Now to find the exact percentile, you'd have to use an applet if it's not on the empirical rules or to get a better estimate. So a mean of 0 or a mean of 100 and standard deviation of 20. And then we're over here at a 130. And you would go to below, and that's the 93.3rd percentile. So to get the exact percentile, you would need to use something like that, where this just gives you an estimate somewhere between the 84th to 97.5th percentile, and this would be the exact, the 93.3 percentile right there. So the applets are used to get exact percentiles, but we should still have some understanding of how percentiles work. That is the percent of area below you on a curve. Does that make sense, Moira, right there? And really good questions. Hopefully that helps with your understanding. It helps you teach other students that the empirical rule can give us some good estimates, and the applets are going to give us exact answers. But you always carry the empirical rule with you when you're just thinking through it. We got 2 more questions here. Thank you so much, everybody. Accompanying manufacturers rivets. Chapter 5, quiz 1. Jesse, thank you so much. You've waited this whole time for this question, I think. Let's do the rivet question. Where is the rivets? Accompanying manufacturers, where'd it go? Oh, there it was. Okay, a company is manufacturing rivets. Oh, you'll do great. You got this, Maura. I have confidence in you. Think Brian has. Do you know how many times I've made mistakes, Maura? You've seen me make mistakes in office hours, so you've seen me get questions wrong. Brian out the applet tonight. So just think, anytime you make a mistake, just smile and say, well, man, some of these questions make an error here. If you make an error, a lot of times I like to ask people where the error is, especially if I see it. Rarely do I not see it. That's usually when I'm like, where is the error? Or I'm like, oh, where's the error? And I'll point to it. It's a good way to make sure people are paying attention. So make some errors. Don't make errors. But if you do, point to them and see if people catch them. We're all going to make errors. I've been doing this for 12 years. Yes, yeah, 12, 13 years over on. A company that manufactures rivets right here has a shear strength between 650 to 40, or 650 of the mean. So all of these have the right mean, standard deviation of 40. So this has the right standard deviation. That's all you're really looking for on this first graphic. And they show you the empirical rules showing the 68, 95, 99.7. Next question says, would it be safe to use these rivets in a situation which requires a shear strength of 610? So 610 is down here at a z-score of what? Very quickly and easily, we should see 610 has a z-score of what? You're welcome, Moira. You got this. 610 has a z-score of what? -1, Jesse. You got it. So think about this. If they require this shear strength, and so this is saying, they're saying we need at least this shear strength. What percent of our widgets will not meet that shear strength? So they're saying if we need at least 610 shear strength, what percent of the widgets? 16%. And what we're doing right here, if 68 is in the middle, 100 minus 68 is equal to 32. And then 16% is the outside portions. So below there is 16%. So very clearly, that's going to be a bit of a problem. So no, because about 16% of the rivets are going to be less than that. What percent of rivets can be expected to be below 730? 730 has a z-score of 2. And once again, problems on the test will tell you to use the empirical rule. And so this problem is showing us the empirical rule, thus we should use it. Do not use the applets for this. Use the empirical rule. And so it says below right, so we're talking that. So close. Jesse's got it right there. It is 97.5 because 2.5% is on either side, making 97.5 below there, or you could add up these values right here, do this right here, or subtract from 100, and another cough drop. So 97.5 is below a z-score of positive 2. That's going to be that way every time using the empirical rule. Once again, do not use the applets for these. The empirical rule is something we can always memorize and use at all times. Now, the last one right here is a little bit confusing. I'm going to reword it completely. So when would you feel safe with a company saying we need a certain shear strength? Now, these rivets are going to be used to like hold up bridges, right? So if a company says we need a shear strength of 800, would you sell them one of our widgets? A company says, and this is like when we expect it to break, and they say we need it to work for at least 800. No, you'd be like, that's insane. If a company said we need a shear strength of 200, would you sell them a widget? Would you sell them a widget if they said we need a shear strength of 200? I definitely would, because our average widget has a shear strength of what? Our average widget has a shear strength, and the strength is how much it can handle, of 650. So would you be pretty confident in our product? Because we should handle about 650 on average. And if you look on the lower end, it's nowhere near 200. So what companies will often do is they'll go 6 standard deviations. 6 standard deviations, which is way off the curve. So if we went down here and went, oh, really? Really? We'll get copy it then. So we're going 6 standard deviations off the curve. So there is 530, standard deviation of 40. How confident would you be down here? So think about this. We're this far away at 410, which if we check the math on this, this is 6 standard deviations. How confident would you be on this? So a standard deviation is 40 times 6. 650 minus that is 410. That is a z-score of -6. Would you agree that a widget that was all the way down here would have to be very, very unusual? Is it likely to see a widget this far away? Is it likely that one of our widgets would have this low of a shear strength? Is that likely or unlikely? That's 6 standard deviations below. I would say that's a very, very what widget? I would say that widget is extremely unlikely. So we could say, you know, we would feel safe at 410 because basically none of our widgets would be that low. And so below, and we'd feel safe selling that to ensure that we never had problems. We can actually find out the exact percentages using R. We might have time to speed run a question. I think it was we're going to speed run a question here at the end. I'm not going to mark it even, I think, because if people stay to the end, you get the secret speed run of it. Using our knowledge from a previous question. So we're going to use our knowledge from a previous question to speed run something here. It was a study was conducted. Is that it? That was shoe size. I thought there was a shoe size question or something. What was the question, Tyler? Do you remember? Jesse. Where is it? A study was conducted. Okay. So this one right here, they're changing it using our previous knowledge from a previous question right here. We know that shifting, here it is right here, shifting will change the measures of center, and spreading and scaling will change the measure of spread. And it'll also change the measure of center. So the standard deviation is a measure of spread, so it's not going to get hit by the shifting. So we go right here. The standard deviation was 1.92. So we're going to times that by 0.7969. Should be right. Wait. 1.02 times 0. decimal errors. 2 decimals. And then the mean will change by both of these. So this is using our knowledge from the previous one. Check out the previous problem right here. And then we're timesing it by it first. There we go. And once again, do check out the previous problem where we went into great detail on this. And we showed examples of how it would change. So this problem right here, 2 language majors, Anna and Megan. Is that on this one? Language majors. Okay, here we go. 2 language majors. Anna scored an 82 on both exams. Megan scored a 79 on the first, 86 on the second. Overall student scores on the first exam were an 84, so Anna was a little below average. Anna's Z-score is 0.5, and second exam was standard deviation at 13. She's got like a point. What is her Z-score on that one? 82 minus 71 divided by 13. So her Z-scores are 0.5 and 0.8. And second exam, overall student. To qualify for language honors, a major must maintain at least an 85 average across all the scores taken. So far, okay, so now you can just look at their averages. Neither qualify, right? Because you have to have an 85 average. So you're literally just looking at the average of these individuals right here. 82 on both exams is an 82 average. Megan scored a 79 and 86. So you have to have an 85 average. So neither qualify. And then which student overall performed better? So Megan scored a 79 and 86. So what you have to look at here is their whats. So what should we look at here, Jesse? We should look at their whats. How would we know which student scored better? So how could we compare them? The Z-scores. Okay. So Anna, her first Z-score is going to be 82. That's about right. Observation. Oh, she's 82 on both. And that's the first. She's above ours there. And she scores 79, 86. Oh, she's going to do worse because she's way more below on the first, I think. So 79, 9 minus 84. And yeah, I think so. It's close. Yeah. If you look over here, she has more of a negative. And then if you add those, that would be a positive number. If you add both of these, that would be a negative number because the negative's higher. So good to see you, Jamel. So it's going to be the first student, Anna, right there. Should be right. Yay. Don't love this question because they should have you find the Z-scores. It's a question that is pretty complex that really they don't walk you through because it's like, okay, well, what would we do? They should say like, what is the proper way to compare these students? And it should be like their test scores or their Z-scores. How could we compare them? Add up their Z-scores and see which had a higher sum of Z-scores. And the student around there on the left would have a 0.34 and the student on the right would have negative 0.10. Just adding up those over here, you'd get positive. And over here, you get negative if you add up these values right there. So they should walk you through a little bit better on this, in my opinion. Mason, good to see you here. We're ending office hours because we got to teach her in a little bit. But that's got it. We did a lot of the problems today. And check it out. Until then, bye for now, everyone. Bye.